Hello everyone. I want to check that my voice is clear. Hello. Okay, thank you. We will start our webinar after 5 minutes, okay? Okay, thank you. Okay, shall we start? Good evening, everyone. It's my pleasure to welcome you all to our webinar, The Life Cycle of Drilling Operations. My name is Sahar, and I will be your moderator throughout this session. So please feel free to reach out via Zoom messages if you have any inquiry or questions, okay? Kindly let me welcome our engineer, Saif Shalabi. He is a certified IWCF drilling supervisor and RTOC engineer with experience in drilling, workover, and well completion operations. Currently specializing in real-time monitoring and drilling supervision of Bebetco, Karen Energy GV. Proven track record of managing high-stakes drilling programs, optimizing rig performance, and maintaining rigorous safety standards in complex environments. We are truly honored to have you, Engineer Saif, throughout this webinar and course. Thank you all and wishing you all a very productive training ahead. Engineer Saif, shall we start?
Thank you, Ms. Sahar, for this introduction.
Thank
Uh,
you.
Hello, everyone, and welcome to this session, The Life Cycle of Drilling Operations. I'm glad you are all here, and I wish you get the best out. And I wish you get the best out of this session and that it will be beneficial for you in your studies or in your work environment. This session aims to give you an overview on drilling operations from start to end. Since the duration of this session is only 1 hour, it will just cover the main topics of drilling operations. Before starting, I would like to give you a brief on me. I'm Saif Shalabi, and I'm a drilling supervisor in Pepetco Chiron Energy joint venture. I have started my career as a workover and well completion engineer, then as an eye drilling supervisor, and eventually as a drilling supervisor. I'm also working as an RTOC engineer in Pepetco Cairo office. You can see my contact information in case you want to reach me for any inquiry or any question regarding this session or in drilling operations in general. So let's start with this session and what you will get from it. This session will basically cover the drilling phases starting from the planning phase, moving on to drilling phase, then to casing running and cementing in place, then to the pre-completion phase, and eventually to the completion phase. Before starting talking about any of these stages, we first need to know what a well is. A well is any hole that is drilled across different formations downhole and is designed to provide a conduit for liquid and gas hydrocarbons to move from the reservoir to the surface. There are many types of wells that can be drilled based on their objective. These types can be an exploration well, appraisal well, development well, infill well, or re-entry well. To talk briefly about each type of these, first the exploration well. It is counted as the first well that is drilled in a specific area. So this area or this field didn't have any well before it. In this case, this exploration well is called a wildcat well. This exploration well objective is to find out whether there are any hydrocarbon reserves in this area or not. In case the exploration well was successful, then we can move to the next stage, which is the appraisal wells. Appraisal wells doesn't only identify if hydrocarbons exist in a specific reservoir or not, but it also identifies the extent and the dimensions of this reservoir. So it's not sufficient to find out whether there is hydrocarbons or not in an area, but it's also mandatory to know whether this accumulation is commercial or not. This is the objective appraisal well, to know if this accumulation is commercial or not. If the appraisal well plan is successful, then we move on to the next stage, which is development wells. Development wells are a group of wells which are drilled in a specific field to get the optimum productivity of this field. These wells can be injectors or can be producers, depend on the development program. Next plan is the infill well. An infill well is a well which is drilled to specifically target a specific accumulation of hydrocarbons in a specific area which was missed by the original development plan. Finally, we have the re-entry well, which is any well that is continued after a specific well was drilled before. So basically, it's not a new well, but it's a continuation to an old well, where we can deepen this well, or we can sidetrack or move this well to a different direction so that we can access different targets that were not accessed before in the original well. Each one of these wells requires a specific plan, and this plan is the first stage of the drilling operations. So the planning phase is the phase number one. And in this phase, it aims to create a program that displays how this well is going to be executed from A to Z. This plan must contain some mandatory parts or some mandatory elements. These elements start with the drilling trajectory and target depth. This describes how the well is going to be drilled, whether it's going to be vertical, deviated, or even horizontal. And it also identifies the target that I want to that I'm aiming to reach in this well. It also requires the specification of casing and cement design, how many sections we are going to drill, what are the type of casings that are going to be used regarding weight, grade, size, and so on and so forth, and how are they going to be cemented in place, and what is the specification of the cement slurry that is going to be used. It also needs to specify the drilling fluid criteria regarding all the mud properties that are used while drilling specific sections. Each section in the well requires different drilling fluid with different criteria. It also needs to specify the PPFG, which stands for pore pressure fracture gradient curve. This curve identifies the adequate or the appropriate mud weight that we need to use. We need to use a mud weight which is not very low so that it can control the formation fluids inside the formation without causing any influx or well controlled situation. And at the same time, it requires that this mud weight is not excessively high, that it will not cause fracturing of the formation. Next is the bed and BHA selection. So out of the variable and out of the multiple types of different beds and different BHA components, we need to specify the specific type of bits and BHA components that will be used in each section drilled in the well. Moreover, we need to specify the risks and hazards that might be encountered while drilling a well, how we can mitigate these risks, how we can even eliminate them completely, and in case of their occurrence, how we can deal with them. Finally, planning phase requires specification of authorization for expenditure, which stands for or which is abbreviated into AFE. This AFE is like a budget or a specific amount of money which is specialized to be used in this well based on each cost that is going to be spent at each stage of the well drilling. After specifying the planning phase, we move on to the first stage, which is moving the rig to the well. And in order to move the rig to the well site must be ready. This is the scope of civil engineering, not petroleum engineering or drilling department. However, we need to understand that after the location is ready, a conductor string must be installed in the rig site. This conductor string can be accounted as the biggest and the widest string and the first casing string that is placed inside the well site. This conductor string is used to prevent the loose topsoil or the shallow formations from washing into the well after drilling it, so that it can provide a conduit for me to start drilling and to start circulating fluid through the hole. There are two ways through which we can fix conductor in place. First one is driving it using hammering effect. This hammering effect is applied until we reach what is called a refusal point. This refusal point refers to a content formation at which no more hammering can drive the conductor deeper because the formations are content and hard enough, so they will not accept any hammering to drive the conductor down. The second way is like any ordinary casing string, by drilling and cementing in place. Once the conductor is ready and in place and the rig is accepted, we are ready to start the second stage, which is the drilling phase. As you can see, the drilling phase involves a drilling bit that is fixed at the end of a drill string, which keeps rotating and applying weight on it so that it can cut into the formation deeper and deeper until a well is created. And while this operation is being held, there is drilling fluid which is circulated through the drilling bit nozzles that helps us to carry the cuttings out of the well so that more and more and more meters can be drilled. In order to start or in order to achieve this drilling action, we need to apply what is called drilling parameters. These drilling parameters are weight on bit. The weight on bit is the amount of weight that I place on a drilling bit so that it can start drilling and acting on the formation and causing their cuttings. The next parameter is the RPM, which stands for the revolution per minute, and it represents how fast the string rotates. The third parameter is the GBM, which is the gallon per minute, and it represents how fast the drilling fluid exits out of the well, out of the bit, and into the annulus. These three parameters yield what is called rate of penetration, or ROP, which is how fast I am drilling, and it's represented by the amount or the number of meters drilled in 1 hour. This screenshot is showing one of the services that are almost provided in all the drilling rigs, especially those which presented in Egypt. This is called the rig sense, which is provided by NOV. And this rig sense shows curves of different parameters and different indications that we can get while drilling. So as you can see from this screenshot, there are so many curves that exist and they are divided into compartments. And each one has the name of the parameters down here with the corresponding colors of each curve. We can see on the bottom that we have the hole depth and the bit position. They will be identical while we are at the bottom or while we are drilling. But if we are tripping, they are going to be different. We can also see the hook load, which represents how much weight the traveling block or the hook is carrying. We can see the block height here. If it's moving in this direction, this means that the string is going down. If it's moving in the opposite direction, it means that the string is going up. We also have the bit weight, which represents of how much weight I am applying on the bit to drill. We have the top drive RPM, which we talked about, the RPM, the revolutions per minute. We have the top drive torque, which is produced by the effect of the RPM. We have the ROP, which is the rate of penetration. We have the flow in rate, which is how fast the fluid is circulated. We have pump pressure, which is the pressure produced as an effect of the flow rate, which is pumping the drilling fluid. We have the flow out percent, which is the speed at which the drilling fluid exiting into the flow line. We have the mud volume in the tanks. We have the trip tank volume, which is used in trips. And we have the gain loss curve, which identifies whether we have losses or gain or we are in a normal condition. After drilling is accomplished, we move on to the next stage, which is installing casing string. And casing can be counted as a large diameter steel pipe, which is used to strengthen the wellbore of the hole or prevent any collapsing of the hole that is already drilled into the bottom. So the casing can be accounted as a structural backbone of the well because it keeps everything in place. Casing can be classified on different factors, for example, the function and size, and we will identify this in the following slides. It can also be divided or classified based on the connection type, where we have two types of connections. We have the API connection and the premium connection. The API connection depends on the dube to do the sealing effect, while the premium connection depends on metal to metal seal to form the sealing effect. We also have classification based on weight. The higher the weight of the casing is, the more or the stronger it is. We have the grade classification, where each grade has different strength properties, including tensile strength, collapse strength, and burst strength. We also have different length ranges for each type of casings. Casing function is not only a structural backbone of the well, it has other functions. For example, it isolates porous formations with different pressure regimes. This means that if we are going to drill a specific section, where we have in this section one zone which has low pore pressure and the other zone which has high pore pressure. If we are going to use the same specific or the same drilling fluid to drill both sections, if this drilling fluid has low mud weight, it will be able to drill the low pore pressure zone without any problems. But when it comes to the high pressure zone, we will have well control issue where formation influx might enter the wellbore. However, if the same drilling fluid has high mud weight, then it will not cause any problems when drilling the high pore pressure zone. However, when we come to the low pore pressure zone, this will cause fracturing of this zone, causing more and more issues. So this is why casing strengths are very important when it comes to zones with different pressure regimes, because we will not be able to deal with both pressure regimes successfully. We will have to account for one zone over the other. Otherwise, a problem may arise. Next is selectively produces from specific perforated formations. So let's assume that we have a formation or a pay zone which contains both gas, oil, and water zones. Of course, it's the correct action to produce the oil instead of the water and gas because water is not desirable in oil wells and gas acts as a driving agent that can force oil into the well. So we need to preserve both gas and water and we need to just produce the oil. So this when it comes to the casing function because it seals all the three bearing zones and when we perforate exactly at the oil bearing zone only oil is produced. It also isolates troublesome zones, like caving shale, for example, like swelling and sloughing reactive shale, like thief zones, like abnormal pore pressure zones. Any type of troublesome zones can be isolated by casing so that we can drill the rest of the well without having to deal with this problematic zone. Next is serves as a high strength flow conduit. And this is what we talked before about because it has high collapse and burst strength and it can withstand the pressures of producing formation fluids to the surface. Casings also prevent shallow freshwater zones from contamination, and this is when it comes to the function of the surface casing in particular, where it prevents the freshwater to be mixed with the drilling fluid and preventing it from contamination. We also can see that function of casing is also providing a connection for wellhead equipment and BOB. This is because wellhead equipment and BOB requires to be fixed to the top of the casing, and hence the top of the casing provides a base for these equipment. And of course, we need BOB during drilling because it acts as a secondary barrier, where in case our primary barrier, which is the drilling fluid, failed, then we will be able to control the well by shutting it in using the BOB until we regain the drilling fluid barrier, which is the hydrostatic pressure. Next is provide smooth conduit for tubular and equipment running, since the casing has constant ID. So it provides constant or unchangeable ID that can help the tools to be installed and pull out of hole without having problems with ledges or with any kind of irregularities in the open hole. There are many types of casings based on the function and the sizes. We can use a conventional layout of casings. However, it may change from one well to another. But in the conventional setout of casing design, we can see that we have four types of casing. The first one is the conductor casing that we talked about before, which is the first and widest string that prevents loose topsoil or the shallow formations from caving into the well. The second type is the surface casing, which protects the fresh water from being contaminated by the drilling fluid. Then we have the intermediate casing, which isolates any type of problem zones. And finally, we have the production casing or liner, which provide a conduit for hydrocarbons to flow into the surface safely. The production casing and liner are different in one important factor, which is whether it's extended to the surface or not. In case of production casing, the casing is extended to the surface, while in case of liner, it's not extended to the surface. It's just set at the previous casing, just above the show by a few meters, maybe 100 meters or something. After installing the casings, we need to fix them on the top. And this is when it comes to the importance of the wellhead. The wellhead provides a connection point for the BOB during drilling and Christmas tree during production. As you can see in this image, we have this flange connection. This is the same exact connection of BOB or Christmas tree. So they can be fixed on this connection and fixed by bolts in flange to flange connection. So it provides the base for this equipment. It's also used to hang tubing and casing strings from the surface, where we install what is called tubing hanger or casing hanger in this groove that you can see on the top of this drawing. This hanger supports the weight of the casing string or the tubing string. It's also used to seal the tubing casing or casing analysis, which means that by installing a hanger in this place, the annulus between a casing and the previous casing will be isolated. And if I want to access this annulus, all what I need to do is to just open this side outlet valve, and I will have an access to the annulus. And in order to have access to the annulus, I can use it in injecting any type of fluid. For example, gas injection in gas lift wells. After installing the casing and setting the hanger in the wellhead, this is when it comes to the cementation or the cementing process. And in the cementing process, it involves pumping cement slurry into the casing string until it exits the casing show and enters the annulus between the casing and the open hole, holding it in place. This is not the only function of the cement slurry. It serves many other functions. As we said, it bond and support the casing in place. It also protect the casing from corrosion, since it isolates the formation fluids from accessing or from reaching the material of the casing. It also provide sealing of problematic zones and restrict fluid movement between formations, where it prevents any formation fluids from exiting into the well or exiting and going to a different formation, causing a change in its pressure regime. Now let's talk about how the cementation problem or how the cementing operation is done in a brief summary. So basically, the first step is that we start by bumping a spacer ahead of cement. This spacer's function is to isolate between the cement and the drilling fluid to prevent the contamination of both. After the spacer is bumped, we start by drawing what is called a bottom plug. This bottom plug acts to separate between the spacer and the drilling fluid and between the cement. Then after bumping the plug, we start bumping the cement slurry itself. After bumping the cement slurry, we drop the top plug. After dropping the top plug, we start displacement of the whole train using drilling fluid. This displacement continues until the bottom plug continues to go down until it rests on its seat, which is called the float cooler. Once it's on its seat, the cement will start acting on it, increasing the pressure above it. Since this bottom plug contains a glass disc or a rupture disc, by doing this pressure or increasing the pressure on it, this glass disc eventually breaks, causing the cement to start moving down across it or through it and into the annulus, cementing the annulus between the casing and the open hole. Now the top plug is going to continue moving down, while the bottom plug is stable in its place until the top plug reaches the bottom plug and rests on it. Unlike the bottom plug, the top plug doesn't contain any glass disc on it, which means that by continue bumping, it will not allow the drilling fluid or the displacement fluid to pass through it, which will cause an increase on the pressure since there is no way through which the fluid or the displacement fluid can exit. This increase in pressure is what is called the pump down plug effect. And this pump down plug is a representation of the end of the cement job. It means that all the cement has been displaced into the annulus, covering the gap between the casing and the open hole. After this is done, we wait for cement for a specific time, which is until the cement is set and reaches its compressive strength. Since the cement is at the beginning a liquid state, then it changes into a gelling state, and finally it solidifies. This is what we are calling cement set, and it's represented by a specific value of compressive strength. Once this is done, then the weight on cement is over. After cementing the casing in place, we have our section ready. We repeat the same exact thing in every section drilled in the well until we reach the TD, which is the total depth of the well. Once we do so, and before moving on to the next slides, I want to just show you a quick brief of how cement job is done so that you can digest the information better. So we are currently drilling the well, and you can see the drilling bit at the end. Here, keep drilling until it reaches the TD, and then we install the casing. Now we pump the spacer, and the bottom plug is at the bottom. The glass disc is ruptured. The cement starts to exit into the annulus. Now we are displacing the cement using displacement fluid until the top plug rests on the bottom plug. And at this stage, the pressure increases, forming the pump down plug effect. Moving on to the next stage, which is the pre-completion stage. And comes after all the drilling stages end, which are the drilling phase itself, the casing running, and the cementation. Then it comes to the pre-completion, which links between both the drilling stage and the completion stage. In pre-completion, there are three major things that are focused in this phase, which are formation evaluation, structural integrity, and wellbore cleanup. We will discover each one of these factors in the following slides. Starting with the formation evaluation, this study aims to find out or to identify whether this well contains commercial accumulation of hydrocarbons so that it can be completed, or it doesn't, and it's called a dry well if in case it doesn't have hydrocarbons or it doesn't get access to hydrocarbons. And in this case, we don't complete the well. We plug and abandon the well, and we will discover both processes in the next slides. So in order to identify whether this will contain commercial accumulation or not, we need to do this formation evaluation study. And it's done by more than a way. We can do it by coring, by open hole logging, by logging while drilling, by formation testing, and by cased hole logging. And these five are going to be explored in the next slides as well. So the first factor or the first process through which we can do the formation evaluation is the coring. And as you can see in coring, we have here on the bottom a drilling bit, but this bit is different from the ordinary drilling bits. The coring bit has like a hole on the bottom of it, so that while it keeps drilling, a core, a circular core, or we can say a cylindrical core, is cut in this process and enters the drill string or the coring string through this hole. As it enters, it goes into what is called a core catcher, and it's prevented from going down again by a mechanism here which allows only the movement of core in one direction without falling back. Once this core is extracted from the drilled formations, it's very important to preserve this core, and this is done by preventing it from drying out or from coming into contact with oxygen or being mechanically damaged. Then after this sample is extracted to the surface, it's transported to one of the laboratories where we can get from it important information like detailed lithological description, porosity information, permeability information, or fluid saturation, and so on and so forth. The next method is the open hole logging, and it deploys a tool string which is run on a wire line or electric line, and these tools log or record some information about the formation that they bypass through it using specific mechanism that is beyond the scope of this course. So this log is one of the most common ways through which we can evaluate formations after drilling, and it's usually done in the reservoir section. Another way is logging while drilling, And this method is very similar to the open hole logging, but the main difference is that the open hole logging is performed on a wire line or electric line, while the logging while drilling is performed with the same tools but deployed on drill string. So it's done in one of two possibilities in most cases. The first one in case that we need faster information. So we deploy these components or these string or these components into the drill string components so that we can get real-time data while we are drilling. So we won't have to wait until we finish drilling the whole section, then pull out of hole, then run in hole with wireline. You get the information the same time you are drilling. And the second instance that we use logging while drilling is when we use open hole logging and the wire line fails to go down to the bottom due to obstruction or due to dogleg or due to high inclination or any reason. Because logging while drilling are run on a string, so their possibility to pass obstructions is higher than wireline. The next way of formation evaluation is formation testing, and this way is done by one of three major ways: wireline testing, drill stem test, or well test analysis. The wireline testing deploys running a tool like the RDT tool on a wireline. This tool is run until it's across the formation of interest, and once a signal is sent by the wireline, these pads go out until it contacts the formation and start to take samples from the formation so that it can test properties like permeability, for example, and even recording fluid samples that can be analyzed in the laboratory. We have also drill stem test, which uses temporary drill string to test the formation. We also have well test analysis that use some concepts like drawdown concept and build up concepts by producing from a well for a specific time or shutting in the well for a specific time, then use some recorded data to get properties like permeability and skin effect, for example. So these topics are generally known as formation evaluation, but I don't want to get into more details about each one of these as it's not the scope of the course. Next way is the cased hole logging, and it's similar to open hole logging, but it's after running the casing. It's not in the open hole, it's after running and cementing casing. And it aims to get data like production logging, which represents um, a profile for production or injection over time. And it can also record information like reservoir monitoring, which identifies the change in the characteristics of reservoir over time. After evaluating a well and identify whether it will be accessing a commercial accumulation of hydrocarbons or it's going to be a dry well. Then comes the other objectives of the pre-completion phase, which are the structural integrity or what is called the well integrity. And in this stage, we aim to identify whether our skeleton, which is the well, the casings, and the cement, is going to hold pressure and flow or not. We want to know in this stage whether our skeleton or our frame is going to leak or not. And this is done by more than a way. The most two common ways are the cased hole logging and the pressure testing. In the cased hole logging, we run logging tools like the CPL, which stands for Cement Bond Log. And without going much into the details of this log, in general, these kind of logs are deployed on a wire line and they use sonic waves to identify whether the cement itself has a good bond to the casing and to the formation or not, and identify whether this cement slurry or whether this cement has any voids or any microannulus inside or not. So in case the cement is good, it will not contain any voids inside. The second method through which we can assess the structural or the well integrity is the pressure testing. And in pressure testing, we close the well using the BOB, for example, and we start raising pressure against the BOB on the whole well. And we check if the casing pressure, for example, is going to hold at the same value or is going to drop. In case it's hold, then it means that we have a good well integrity. Otherwise, if it's dropping, this means that we have a leak downhole and we have a problem that we need to be investigated and fixed. The third purpose of pre-completion phase is the wellbore cleanup. This is done because during drilling, we use a drilling fluid which contain many chemicals and solid particles that may cause formation damage in case the formation is exposed to it. So it's mandatory to perform this wellbore cleanup before exposing the formation through perforations or any other alternative method. This wellbore cleanup can be done in both mechanical and chemical ways. In mechanical ways, we are using tools like scrapers and brushes that can scrub the inside diameter of the casing and hence provide clearer and better pour so that we can set tools like packers and we can also have cleaner well. The second method is the chemical displacement. And in chemical displacement, we just change the type of the fluid in the well. Since we have drilling fluid filling the whole well, if we perforated the casing and we accessed the formation to start production, this drilling fluid will start to invade inside the formation, causing its particles and its chemicals to block the pores and causing formation damage. This is why we displace this drilling fluid with a brine. And this brine is composed of water, salt, and chemicals that are non-damaging to the reservoir. So this brine is a clearer and cleaner fluid that will allow us to produce, to access or to perforate into the formations without causing damage to them. After cleanup ends, we reach to the final stage of drilling a well, which is well completion. And in this stage, we adjust and we get the well prepared to produce hydrocarbons. This stage or this phase is a course on its own, so we will not go deep in it. We will just figure out the main components and the main equipment that are used during the well completion. And these components can be classified into four major components. The first one is the production casing or liner, second one is tubing, third one is tubing accessories, and the final one is Christmas tree. The production casing or liner we discussed before, so you may wonder why I placed it in the well completion. This is simply because the production casing or the production liner is not installed until we make sure that the well is going to be completed. So let's assume that we have made our formation evaluation after drilling all the sections of the well, and we found out that this well is going to be a dry well. This means that there will be no production casing or liner installed in the first place because it's counted as a part of the well completion. It's installed only in case we are going to complete the well. The other three types are going to be discussed in the future slides or in the next slides. So the first equipment after the production casing or liner is the tubing. And the tubing, we can count it as very similar to the casing strings, but there are some differences. These differences include the sizes. The tubing is smaller. It includes the grades. It's weaker than the casing. And most importantly, the tubing is temporary and not permanent as the casing. So as we discussed in the casing before, these strings are cemented in place, which means that they are fixed in the well, maybe in the whole lifetime of the well. So in case we produced through these casing strings, this means that the production flow stream, which contain abrasive solids and some corrosive elements, may cause these casing strings to be corroded or to be eroded, and it will be very difficult to repair this damage or to replace this casing. This is why we are using tubing because it's replaceable. It's okay to be damaged because its replacement is easier than the casing. The tubing string is fixed on the top by a tubing hanger and is fixed on the bottom by a packer or production packer. These tubings have smaller diameter, so they provide based on the continuity equation, which says that A multiplied by V is constant. A is the cross-sectional area or the flow area, and V is the velocity. So since this multiplication is constant, this means that as the area gets bigger, the velocity gets smaller and vice versa. So since the tubing string is smaller in size than the casing, this means that the velocity inside the tubing is going to be higher, which will help to rise or to carry the formation fluids into the surface. And in case they are corroded or damaged for any reason, they will be replaced easily by unsetting the hanger on the top and the packer on the bottom and just pull out of hole and replacing it with a new one. Next is the tubing accessories. And in tubing accessories, we can see that it contains huge variety of accessories. So we are going to talk just about the basics. For example, the production packer, which is here, this element. This packer acts to seal the annulus between the tubing and the casing. This helps to prevent the formation fluid from entering the casing and hence protect it from corrosion and erosion. Next is the landing nipple. The landing nipple acts as a seat that allows us to set different tools in it. We have here the landing seating nipple and the no-go nipple. The landing seating nipple contains like a groove inside, and any other downhole tool which contain the same groove will be set inside. Think about it like as a key and a key seat. If the profiles matches, then the key will enter the key seat. This is the same exact concept. If the tool itself have the same profile as this landing nipple, it will land in it. While for the no-go nipple, it may contain a groove like the landing nipple, but it contains another feature, which is the no-go section. This no-go section is a reduced diameter section. So in case this downhole tool that you want to set or to place downhole doesn't contain a profile, it can be set by just landing on this no-go or on this restricted ID section. Next is the sliding side doors, which are this port, the SSD. This SSD can be counted as an on and off switch, which allows the communication between the tubing or the inside of the tubing and the casing. So in case we have like any drilling fluid or any formation fluid, sorry, which is inside the tubing and I want to get it an access to the annulus, I can just switch the SSD open and it will enter from here up to the annulus. And if I want to cancel it, I will just switch the SSD off so that it will return again to move in one direction up to the tubing. Next is the blast joints. The blast joints are thick joints that are placed in front of perforations because in perforations, the formation fluid usually exit with a high velocity and carrying abrasive particles that may cause erosion to the OD of the blast joints or the OD of the tubing. So the blast joints have thicker diameter so that it can withstand this erosion effect. We also have flow couplings, which exist around any restriction in the tubing because they transfer the turbulent flow into laminar flow and hence reduce the erosion but to the inside of the tubing. We have the solid control subsurface safety valve, which acts as an emergency valve that will be activated if any problem happened to the surface equipment, so it will just shut in the well immediately. We also have the side pocket mandrels, which accommodate um, gas lift valves that are used in gas lift operations to inject gas into the annulus and help to carry the production stream to the surface. Finally, we have the wireline entry guide, which is the bottom part in here. And this wireline entry guide acts to facilitate the entrance of any tool string that is used. So let's suppose that we have a wireline or stick line, which is installed inside the tubing, and the tool string is out of the tubing. Then when we pull out of hole again, this tool string, when it tries to enter the tubing, it will just have an obstruction due to the rounded edges of the tubing. However, if we have this wireline entry guide or what is called the mule shoe, then it will be able to facilitate the sliding of this tool string inside the tubing and pull out of hole easily without any troubles. Now moving on to the final equipment of the completion stage, which is the Christmas tree. As you can see, the Christmas tree is composed of different valves and gauges that will allow us to control the flow in or out of the well. This part is the wellhead, this part below is the wellhead, and this part from here is the Christmas tree. You can see these two valves. These two valves on the bottom are the master valves. They act to switch on and off the accessibility to the well, whether it's production or injection. If they are closed, nothing is going to pass in or out of the well, and vice versa if they are open. We have two valves because the bottom valve acts as a backup for the top master valve in case it had any problem or it need maintenance, so that we can shut in this valve so that this one on the top will be repaired. This one on top is called the upper master valve, and this one is called the lower master valve. We also have the kill wing here, which allows us to inject into the well. We have the production wing here, which allows us to control the production out of the well. And finally, we have the swab valve, which allows the entrance of well intervention equipment into the well without having to shut in the well. Now moving on to the plug and abandon, which is the scenario that we have to follow in case the well failed. When by failed, I mean in case it's a dry well. So of course, if it's a dry well, this means that it doesn't contain any hydrocarbons, and it won't be wise to consume more money on it to install completion equipment. And this is when it comes to the plug and abandon scenario, or what we call the P&A. And we do this plug and abandon because if the well is to be left without completing, then it has to be shut in because it's not safe to leave it open. Yes, it's not producing, but there are development plans in the field. And of course, there are injector wells. These injector wells cause manipulation of the downhole pressure that may shift this well to a producer at some time. And if it's not closed, it may cause this formation fluid to exit from the formation and enter to different formations, causing change in the pressure regime, or maybe even cause the formation fluid to exit out of the surface, causing a disaster. And this is why we have two scenarios, either to complete the well or to plug and abandon it. But we can never leave it open, even if it doesn't yield any hydrocarbons. And by saying plug and abandon, we mean plugging it with cement in most of the cases. Cement plugs are used to seal off the well and all the producing formations down below. We can summarize the steps of the P&A into the following. The first step is pumping cement plugs at strategic depth. We have three types of cement plugs. The first one is the reservoir plug, which is set across or above any producing zone or any pay zone. This prevents formation fluid from exiting this zone, for example, and enter a different zone or going out to the surface. The second type is the T-plug, and as the name implies, this T-plug looks like a giant T letter because a part of it is above the packer of the top of liner, and the part of it is below the packer of the top of liner. So you can see that it forms a T shape. And why we said this type of cement plugs? Because this top of packer or top of liner is always a potential point of leakage. So if this point leaked, this means that even if this part is sealed, formation fluids may enter through this top of liner, causing entrance of the formation fluid and even evolution of it to the surface. The third type of plugs is the surface plugs. And the surface plugs are set at shallow depth so that they act as a secondary barrier to the below two plugs in case one of them failed. Once we set these plugs, we need to make sure that they are working efficiently. And this is done by two methods. The first one is by tagging on this plug. By tagging on the plug, we run in hole again with the string that we used to pump the plug and make sure that we slack on this plug, which means that it's hard enough that it can carry a drill string or a cement string, which means that it's competent and it is reliable plug. The second type of confirmation is the pressure testing, which is after the plug is set, we raise pressure above it to make sure that it will hold this pressure, which means that it will most probably hold the pressure down below as well. After doing this and making sure that the cement plugs are set and are competent enough, we had to remove the upper sections of the casing for future usage in different wells. After removal of the upper casing sections, we'll also remove the well head so that it can be used in future wells. And of course, we will not leave the well open. So we weld what is called a steel cap on the top. So now we have three plugs at least, because this plug may be more than one plug based on the number of pay zones. And we have also the steel cap. This is a confirmation that the well has been abandoned successfully. Now, after finishing all the parts of the drilling operation phases, we reach to the end of this session, but we will just recap quickly all these phases in one single video so you can see exactly how it starts and how it ends. So this is the rig site, as you can see, and it's still there is nothing have been done. The first thing done is digging the cellar, which gives us a height that will help us to accommodate the wellhead and the BOB equipment. After digging the cellar, we start installing the first casing string that we talked about before, which is the conductor casing string. And this is the widest and the largest and the first casing string. It's inserted or installed into the well using one of two methods, as we said before. The first method is either hammering this conductor string into the formation until the refusal point, or by drilling and cementing this conductor casing in place. Once this is done, we can make this conductor as a base to what is called a diverter. This is a mistake in the video. It's not the BOB system, it's the diverter system that is installed on the conductor. Then we had to drill the 17.5 or the surface hole section. After drilling the surface hole section, we install the casing and we start the cement process. Then we wait for the cement to set like this. And now we have finished the first section of the well. This is when we nipple down the BOB and we start to install the wellhead or the first part of the wellhead, which is the casing head housing. There are so many types of casing head housings, but this video shows the type which is called the slip and cut type that we will explain now. This is going to be the final shape of the wellhead, but it's not installed one time. It's installed one at a time. So at the beginning, we will install this part in the bottom, which is the casing head housing. This is done by the slip and cut method, as we said, by cutting the excess casing, then weld the casing head housing on the top of the cut surface casing. And now we have the foundation of the BOB. So this casing head housing is welded to the top of the casing and resting on the conductor. Now we nippled up the BOB, but we need to make sure that this connection is not going to leak. So we need to pressure test it. This is done by installing what is called a test plug into the groove of the hanger of the next casing string. Then we are going to raise the pressure from the inside to check that this part is not leaking. After it's done, the test plug is retrieved and we are going to install what is called a weir bushing. A weir bushing is a part that is installed inside the groove of the hanger that is going to be installed in the future to prevent it from being damaged by the rotating string while drilling the next hole section. So now we are ready to start drilling the intermediate section. This is the drill bit with the BHA and the drill string. Now it will drill the plugs that were there before because they are drillable and the rest of the section. Then we installed again the intermediate casing, we cemented it in place, and then we are going to wait for the cement to set. And now we are going to repeat again the surface work. We are going to nipple down the BOB once more. Then nipple up the casing head spool. And before doing this, we will install the hanger of the intermediate casing to fix it in place. Then we are going to cut it and install the casing head spool. And now we are going to repeat the same exact thing. We are going to nipple up the BOB and test the connection by installing the test plug. Then if it's successful, we are going to retrieve the test plug again and install the weir bushing as we did before to protect the groove at which the hanger that is the same as this hanger was installed in the future to carry the future casing of the next section. Now that weir bushing is in place, we are ready to continue drilling the final section, which is the reservoir or the pay zone section. Now the drill string is ready, we will start drilling the plugs again of the cement since they are drillable, and we will drill into the new formation of the reservoir section. Then we will install the production casing or the liner, cement it in place, and wait for the cement to set. Now we will nipple down the BOB, install the hanger so that it will be fixed from the top, then cut the production casing and install what is called the tubing head spool. It's called like this because it's specialized to carry the tubing hanger, which is going to carry the tubing itself. And now we nippled up the BOB, and this option and this stage is not mandatory. It's optional based on the objective of the well. Because now we are going to drill just the show track or the plugs of the cement and drill a few meters as a rat hole. So this is optional because it's not in all drilling wells. It may or may not happen based on the target depth and the total depth or the TD. So we may cancel this stage based on the well objective. And now guns have been installed and perforations were done across the casing. And now the final completion is going to be installed so that the well will be ready to produce. After this is done and all the tubulars are in place, then there is no more need for the BOB. So we install the tubing hanger and we nipple down the BOB. Then we nipple up the Christmas tree. And now you have your whole well ready to produce. So this was basically all the steps of drilling a well from planning phase to completion phase. And that's it for this session, guys. If you have any questions, don't hesitate to ask me.
Thank you, Engineer Saif, for this grateful and great session. Please, if you have any question, can you write it in this chat box?
There is a question from Muhammad Hassan saying in the animation why there is an open hole below the production casing. This is a good question. And as I said, it's an optional stage or an optional step because it depends on the TD, which is the total depth and the depth of the target. So in each well, there is a criteria for the target and for the total depth. And why is this? Because in any well, we need like a rat hole, and this rat hole is specialized to carry any fill that is produced while production. So this rat hole must have a minimum depth. If this depth is not reached by the liner or the production casing, then this means that we need to extend drilling to a few more meters until we have the minimum meters of the rat hole so that we can divert the well to the production. Another question, why don't we use the cup tester instead of test plug? Actually, each one of them has a specific usage. The test plug is used to only test the BOB and the connection, because you may test the BOB to higher pressures than the pressures that you are going to test the wellhead with it. The wellhead may be rated as 5K pressure, while the BOB may be rated as 10K pressure or even 15K. So the test plug isolates the wellhead completely and make the pressure test only on the BOB and on the connection between the BOB and the wellhead, while the cup type tester is set inside the casing, allowing the pressure test to even reach the wellhead. So in this, it depends on the type of the test you are doing. If you are testing the wellhead, you are going to use cup type tester. If you are testing the BOB only, you are going to use test plug. Another question, what is the weir bushing and why we are using it? The weir bushing is a piece of equipment that is placed in the same groove that the hanger, whether it's a hanger for casing or a hanger for tubing, is placed. Why is this? Because during drilling, the rotation action of the drill string may cause the drill string to hit this groove. And by hitting this groove continuously, you may cause this groove to be weird. So the groove in the future will not be able to carry the hanger since it has been distorted. So you place the weir pushing during drilling to protect the groove at which the hanger is going to be placed after finishing drilling. Someone is asking, is the lecture recorded? Yes, I believe they are recording the lecture.
Yes, it's
Uh,
included.
Someone is asking why are mobile phones to be switched off during perforation? Actually, it's not always switched off during perforation. It's only in case you are going to perforate using a wire line or electric line, because there may be interference between your mobile signal and the wire line, which may cause the guns to perforate or to fire before the determined depth. So it's basically to just prevent any interference between the signal and the wireline signal. Uh, I am I am pleasured with your thanks. The rat hole is left as open hole. Yes, exactly. The rat hole is left as open hole, but actually in the company I'm working at, we usually don't extend. We are just drilling the reservoir section, and after we doing so, we take into account the rated or the required rat hole, so that we will not need to deepen the well from the first place because we already left a good enough rat hole at the beginning of the planning phase. However, if for any reason during operation, like any problem with your casing tally or your casing is shallower than expected, you will have to extend. So it's basically dependent on how many meters you left in your rat hole in the first place and whether this is going to be sufficient as a rat hole or not. You are welcome. Regarding the B&A, how to check the cement blocks are good and sealing, is there a minimum length? Actually, to first start with the minimum length, yes, there is a minimum length, and it depends on the procedures or the manual of the company, of each owner company. From the company I'm working at, the minimum length is 150 meters, but it's varying based on the company policy. Uh, Regarding the part which is saying how to make sure the cement blocks are good and sealing, as we said, these are two methods. The first method is by tagging. By tagging means that you run in hole with a string and you leave the weight, some weight of the string on the plug, and you make sure that it will hold the weight. It will not fall or it will not cause the string to go down. You are slacking the weight of the string on the plug successfully, which means that it's hard and it's carrying some of the weight of the string. The second method is by raising pressure. And by raising pressure, if the pressure stayed at a high pressure without dropping, this means that this plug is holding pressure and it's not leaking, which means that it's completed enough. Thank you so much. Thanks. How do we know if the plug is pumped? We know this by the pressure regime. So you are pumping cement, you finish the cement, you drop the top plug, you are pumping the displacement fluid. When when we got bump down plug, this means that the top plug set on the bottom plug. And since the top plug doesn't have anything through which the fluid will pass through it, this means that the pressure is going to raise because you are pressurizing over it. You are pressurizing a fluid that cannot pass through it. So you will find that pressure is suddenly increasing. This is the indication of pump down plug. You are welcome. Okay, the surface control subsurface safety valve and the blast joint. For the surface control subsurface safety valve, it's a piece of equipment that is that's held open by the means of a control line. This control line is linked to the surface equipment, and this pressure keeps the surface control subsurface safety valve open. If let's say that there are any problem happen to the wellhead, this pressure in the control line will by nature got bleeded. And when it's bleeded, the valve of the surface control subsurface safety valve will automatically close since this pressure that held it open is no longer existing. And for the blast joint, it's a normal joint but has thicker outer diameter. So this outer diameter or this joint is placed in front of a perforation. Why is this? Because in the part the perforation exists, the fluid usually go out with a high velocity, and it usually carries like sand particles and other particles that may cause erosion due to the high velocity. So this blast joint is thick, so it can withstand the erosion effect since it has more material in its OD. It's like a thicker and stronger piece of equipment which is placed in front of the perforated zones to allow more erosion to happen without causing failure in the tubing. Can we get the PDF? I believe Miss Sarah will organize this with you. Why was reservoir perforated before rigging Christmas tree up? Well, this depends. In case the perforation is going to be held on the drilling rig, then this means that you are going to perforate before rigging up the Christmas tree. However, some companies prefer not to do this on a drilling rig because the drilling rigs have expensive daily rate. So they prefer that only the drilling rigs install the tubing and then it moves to another location, then a smaller rig, which is the workover rig or even rigless activities, will do the perforation. So in the first case, if the drilling rig is the one which is going to do the perforation, then you will have to do the perforation first before rigging up the Christmas tree. However, if a workover rig or if the perforation is going to be held rigless, then the Christmas tree is going to be nippled up before the perforation takes place. Thanks so much. Thanks. Appreciating your kind words. Thank you so much. I think I answered all the questions. If I missed a question or any question of anyone, please repeat it in the chat box, and I will be happy to answer it.
Engineer Safe, can I stop recording or wait?
I don't find any question. There is a question about logistics as well, about the certificates, but for me, there are no technical questions left.
About the certificate, it will be generated on our website tomorrow maximum, inshallah. Is there any inquiry or question? Okay, thank you all. Thank you, Engineer Safe, for your time and your valuable material. Thank you. Thank
Thank
you
you
all
so
for
much,
attending
Mr.
this webinar. See you again, inshallah. Okay? Bye-bye.